Hello, Yasin. How are you today?
Good, and you?
Thank you. Could you please let me know whether your professor has started to teach you the influence matrix?
Um, I seriously don't know because I didn't assist last class, so I wasn't present, so I have no idea what he did in class.
So
Really sorry about that.
I think you have already finished the Lagrange, right? Your
Sorry?
prof. How about the Lagrange?
Yes, Lagrange we did.
Okay, the next step is influence matrix. We already solved all the problem related to the Lagrange. And
Not all of them, but I'm working on it this week.
pardon?
Not all the problems, but I'm working on it this week.
Okay. So in the last session, I finished all the problem for the Lagrange.
Yeah, I saw that.
And also I solved other question. There was another problem. I guess 7.14. I just simply this is the only one that I just skip it last session. Let me finish that, and then I will start influence matrix.
But I don't mind if you want to start the influence metrics. I'm gonna learn it on the way, and
Okay, no problem. So because we already solved 7.14, we already solved in the chapter 3. So I can just very fast I summarize it, and I will go for influence matrix. So just very quick 7. Seven point 14. Oh. Okay, stiffness. There's a system at the rest is like this. As soon as you apply a theta, and this is x1, x2, L, x2 is x1, delta x, x2 minus x1, or should be positive. It's better to say L minus x, x1, L minus x. So the problem is just related to the virtual work 7.14, and we are supposed to derive the problem 7.14. For the system, determine the equilibrium position and its equation of vibration about it. A spring force is 0. A spring force is 0 when theta is 0. So there is a static problem. Basically, when we are heading in this problem, it is better to go for virtual work. we did one in the chapter 3, and so this system at the rest, once we release the system, the weight of these two bar is located in the middle. So we have two mg, basically mg here in the middle. So this length is y over 2 if it is y. This angle is theta. So if you take a look at here, and this is going to be basically x. Okay, x2 is x. So x2 x. So here, if you take a look at here, you could easily say relate theta to the x is L cosine theta, y is L sine of theta. The length of this length is L at first. L cosine theta is x and L sine theta is y. So once we release the system due to the mass of the two bar, the system will stationary at theta equilibrium, theta E. Theta sub E lets theta equilibrium, and so once you have these two, you could obtain the variation delta x minus L sine of theta E delta theta, and delta y is positive delta theta L cosine theta. So according to the principle of virtual work, summation of all virtual work is going to be 0. So simply there are two mg, 2 multiplied by mg multiplied by 2 delta y over 2. So each bar is just deflected as half y. So this is a potential work. And also there are two spring force at delta x. Force, virtual displacement, and virtual work is going to be 0. Therefore, if you plug in delta x and delta y from the above, you will reach to this point that mg cosine theta equilibrium. Because we have to assume that at this position, at the rest, theta E is the equilibrium static position. That's why I call it theta E, mg cosine theta E minus multiplied by delta theta minus 2 minus 2 F spring sine of theta E multiplied by L variation of theta is going to 0. If we divided the two sides of this equation by cosine theta, then we reach to this point. Tangent of equilibrium theta is going to be mg over 2 spring force. And FS, you are supposed to plug in like this. FS spring force is stiffness delta x at first it was L, and at the second position is X. L minus X is the total deformation applied to the spring from, and you can also plug in for the X. X is L cosine theta. So K L minus L cosine theta E. So if you take a look at here, if I insert theta E as 0, therefore Fs is 0. So it already satisfied the. So how we could find basically a static equilibrium theta. So we have already reached to this point, theta E is equal to 2mg mg divided by 2kl. If I plug in Fs 1 minus cosine theta E, I just factor out L. So how can I find theta E? So this is nonlinear equation basically from both hand side. So it cannot be easily solved for theta E. The second solution, the second approach for finding theta E, apart from analytical solution, which is very difficult, the second method is just giving arbitrary number, arbitrary theta E, and check left side and right side. As soon as you notice the left and right side is more or less the same, your guess was correct. So solve by trial and error. Trial and error. Just give some theta and to see if you could find the theta E for given value of mg over 2kl. So mg over 2kl we are assume is given, or you could assume number and just give a number for theta E and then go for theta. So I hope you will solve some problem for Lagrange, which is very important. And I already solved a very important question in the Lagrange. And in the next part, we are going to go for influence matrix coefficient. Coefficient A, which is inverse of a stiffness. Basically, K is inverse of. So in some problem, it is easier to find influence matrix rather than go for finding a stiffness, and you could easily construct the equation of motion in a simpler way. K x is equal to 0. So rather than obtaining K, you could go for A and then take inverse, and you will find a stiffness. So generally, if I compare two cases like this, suppose there is a stiffness K1, mass M1, and K2, M2, M3. So K3, so K1, K2, K3, compare with another system like this, K1, M1, K2, K3, K4, and there is a constraint here. So in the left system, generally when once the constraint is one side, it is generally simpler obtaining influence matrix, and when two sides of a system is constrained, it is generally, it is not always, but generally it is simpler to obtain K. But in the exam, you will be exactly asked to obtain A or K, or by the way, you have a choice. If you notice, this is easier to obtain K, you can take inverse and then obtain influence matrix. But in the exam, I'm pretty sure you will be definitely asked exactly what you're supposed to do, what you are supposed to do. So let me describe you how to simply determine the flexibility matrix. So let's focus. So question 6.18. So we are supposed to find the flexibility matrix. Is a stiffness K, M1, K2, M2, K3, M3, K1, K2, K3. So the displacement of each mass can be represented by x1 mass 2 by x2 and mass 3 by x3. So we are supposed to, so when to find the flexibility matrix. So since we have three masses in our system, we are facing with 3 degrees of freedom. So therefore, you can draw a conclusion that the influence matrix is 3 by 3 dimension. The dimension of this matrix would be 3 by 3. So this is going to be A11, A12, A13, A21, A22, A23, A31, A32, A33. So what is the definition of Aij? Aij, it means deformation, displacement at I when there is a unit force at J. So this Aij is translated as displacement at I when there is a unit force at J. When we have a unit force at J, it means so. And also for filling out the influence matrix, you have to be careful that you can easily take advantage of reciprocity theorem for linear elastic system, where Aij is Aji, and also Kij is Kji, and So you know that F, the force in the spring is Kx, right? So when if force is unit, therefore displacement would be 1 over K. So 1 over K would be the displacement if there is a unit force. So in order to fill out this influence matrix, we always start with the first column. We always start with the first column, and then we will go for filling out the second column, and then at the end we will go for filling out the third column. So you have to draw the 3 by 3 matrix. So the first column would be A11. So the first column, it means that A11, A21, A31. So when there is a unit force at 1, what is the displacement at mass 1, which is A11, and what is the displacement at mass 2? It means A21. A21, it means displacement at mass 2 when there is a unit force at mass 1, and displacement A31. So in this case, we are assuming that F3 is 0, F is 0 here. There is no external force specifically applied to the mass. External force at mass 2 is 0, external force at mass 3 is 0. We have only one external force at mass 1. So,
sorry, let me just
yes.
say it again. For example, for A31, we're looking for the displacement of mass 3 if we do a unit force at mass 1, right?
Right. You know, sure. For the first column, A11, A21, and A31 for the first column. So you have to only apply unit force at mass 1. There is no any external force at mass 2 or 3. There is only one force in the whole system, just one at mass 1. And as soon as you apply the unit force at mass 1, the resultant displacement at mass 1 is called A11, and the resultant and the displacement at mass 2 due to the unit force applied at mass 1 is A21. And the displacement at mass 3 is translated as A31, which is a displacement at mass 3 due to the unit force at mass 1. So this one can be translated A21, displacement at mass 2 due to unit force at mass 1.
So if I say A23, so displacement at mass 2 due to force applied at mass 3.
Exactly, unit force, exactly.
Okay.
Exactly. So at first step, we will go for filling out A11, A21, and A31, which is a unit force at mass 1 for all of them. We apply unit force at mass 1, and we will see what is the displacement at mass 1, 2, 3, which is translated as A11, A21, and A31. So if I apply unit force at mass 1, I have here, if I want, here it's better. So F is K1, X, so 1 here, K, A11. So A11 would be 1 over K. Basically, X1. And we know that since the system is a series of springs, and the total deformation basically is, the total deformation is x1 plus x2 plus x3. And x is F over K equivalent. So it's going to be x1 is F1 over K1 plus x2 is F, the only force is passing through all the masses is only F1, right? So F1 over K2 plus F1 over K3. So X, so here it is just X, Therefore, X I would be 1 over K1 plus 1 over K2 plus 1 over Ki. So first, so here, so the first one is very simple. The displacement at mass 1 when there is a unit force 1. So here I simply wrote F is Kx1, x1 is A11. So F is unit 1 and K and A11 is displacement, which is 1 over K. So you can simply fill out here 1 over K1. 1 over K1. So 1 over K1 is the displacement at mass 1, right? So 1 over K1 is the displacement at mass 1. So since there is no any constraint at the end of the mass tree, as soon as you apply unit force, not only the first mass will displace toward down as 1 over K1, the mass 2 and the mass 3 will displace as 1 over K1 because there is no any constraint at the end. So therefore you could easily say the displacement at mass 2 is also 1 over K1 and 1 over K1. It's just very simple. So at first step, I just inserted a unit force at mass 1. F is Kx, F is unit, and displacement, which is A11, is 1 over K1. So M2 and M3 will be therefore displaced as 1 over K1. Before going further for filling out the second and third column, you have to use reciprocity theorem. Reciprocity theorem for linear elastic system, it can be proved that the work done by series of force at displacement 1 at displacement I would be the same as force applied by second series of force at displacement at J. So since there is a linearity, no matter at which direction you apply the external force, the work would be the same. That's why Maxwell theory and Bette's law proves this law. And you are not supposed to prove this law, you have to just use it. Aij is Aji, and also Kij, reciprocity theorem is equal to Kji. So this one, the second column is, this is A12, right? Which is equal to this one, A21. You are not supposed to calculate A12, just simply insert AK1. And also this one, A22, A22, no. This one, A13 is equal to A3 A31. So we already obtained A31 here. So we are not supposed to go for this one. So just simply 1 over K1. So the second step is just you have to go for A22. That's it. A22, it means displacement at mass 2 when we apply a unit force at mass 2. So in the second case, we have to say there is a zero force here, there is a unit force at mass 2, and zero external force at mass 3. So when there is a unit force at mass 2, what is the displacement of all masses? Principally, we are going to calculate the A22 displacement at mass 2. So if I draw it here, simply K1 mass M1, K2 M2, and K3 M3. So there is a unit force. So these two springs is series, right? So X22 or A22 would be X1 plus X2, right? Displacement at mass 1 plus displacement at mass 2. So X1 is 1 over K1 and X2 is 1 over K2. Because in the series spring, the force will be transferred and applied at each masses, the unit. So the displacement at mass 1 is 1 over K1, and this displacement at mass 2 is 1 over K1. And the total displacement at mass 2 would be 1 over K1 plus 1 over K2. So here, just say 1 over K1 plus 1 over K2. So if you take a look at here, if the total deformation of mass 2 is 1 over K1 and plus 1 over K2, since there is no any constraint here, mass 3 also will displace as 1 over K1 plus 1 over K2. So just simply, you have to say 1 over K1 plus 1 over K2. And similarly, according to the reciprocity theorem, I can easily fill out this term without any calculation. A23 is equal to A32. So therefore, I can say 1 over K1 plus 1 over K2. And the last step is just applying, the last step is just finding A33 displacement at mass 3 when there is a unit force at mass 3. So here, at the second case, there is a zero force here and unit force here. So when there is a unit force at mass 3, the deformation is 1 over K1 plus 1 over K2 plus 1 over K3. Why? Because as soon as you put unit force here, this force will be applied also at mass 2 and 1. So F is Kx, F is 1, X is 1 over K. For mass 1 is 1 over K1, for mass 2, 1 over K2, and for mass 3, the relative displacement is, the individual displacement is 1 over K3. However, the total deformation which M3 will experience is 1 over K1 plus 1 over K2 plus 1 over K3. So you can easily fill out the last step as 1 over K1 plus 1 over K2 plus 1 over K3. So this is how you have to obtain the influence matrix. So if you have any question, just let me know.
If actually, if is there any special occasions where the principle of reciprocity doesn't apply?
No, for all of the problem in this course, we are dealing with linear system. In the linear system, you could easily ask me A, I, J is always equal to AJ1. Always, for linear system.
Okay.
You can always use this theory, either for a stiffness or for influence matrix.
Okay, perfect.
So at the end, you can also say that M x double dot plus K x is going to be 0 external force. So x double dot is minus omega squared x plus kx is going to be 0, therefore minus omega squared m plus k x is going to be 0. Therefore, you could say k x is equal to omega squared m x. If I multiply both sides of the equation by k inverse, then displacement from the left is going to be equal. K inverse is basically influence matrix, and mx, which may be used for obtaining the natural frequency and displacement. So therefore you could obtain the equation of motion in matrix format. Or x1, x2, which is just extra information. What we are done with influence matrix, omega is 1 over k1, 1 over k1, 1 over k1, 1 over k1, one over k2 plus 1 k3. Is it okay? K1 and 2. K1 and 2. K1 and 2. K1 and K2. K1 plus K2. And 1 over K1, 1 over K1 plus K2. K1 plus K2 plus K3. M 0, 0, 0, M 0, 0, 0, M3, X1, X2, X3. So just briefly, it's the equation of motion as we already obtained in the previous chapter like this, and you could obtain A and take inverse and just insert K. But generally in the exam, I don't think so you will be asked to obtain a 4x4 inverse of a 4x4 matrix or 3x3, but it is better to know at least how we could relate a stiffness to the influence matrix. Maybe there is an application for obtaining the equation of motion, but simply you have to know how to fill out it, to write and fill out this displacement, influence matrix and a stiffness boards. You have to know how to fill out the two. So the next problem I would like to solve a stiffness problem, which is the same approach. So in the chapter 6, section 6.31, so briefly I'd like to explain. So spring 1, mass 1, x1, x2, mass 2, K3, M3, K4, X3, X2. So how we could basically find the stiffness matrix here. So we have basically three masses. So we are dealing with 3x3 stiffness, 3x3, K11, K21, K31. The first column. The second column is K12, K22, K32, and the last column is K13, K23, and K33. So the same approach, similar approach can be applied to obtain the stiffness matrix without any calculation, without using second Newton's law or anything else. You can easily fill out the stiffness matrix by just merely taking a look at the problem. So for the stiffness, we could take advantage of, again, second Newton's law. F is Kx. So basically Kij is defined as force at I when a unit displacement is applied at J. This is going to be a stiffness at Ij. It means that F is Kx1. So if the displacement is unit, therefore F is equal to K multiplied by 1, which is going to be K. So you could say that in order to find K, I can find F, right? If you apply a unit displacement. So similarly, for the first column, for finding the first column, we have to apply a unit force, unit displacement at mass 1, a unit displacement at mass 1. So what would be the resultant force F1? What would be resultant force F2? So it is going to be K11, K1, K3, 1. So displacement at mass 1 is 1, while we have to make sure displacement at 2 should be 0 and displacement at mass 3. For writing the first column, like this is the same as similar to influence matrix. We were only applying unit force at mass 1. Here we only apply a unit displacement at mass 1, and you have to make sure the displacement at mass 2 and mass 3 are 0. This is the principle for this is a principal approach for finding basically F1, F2, F3. It means K11, K21, and K3. So the first column, K11, K21, and K31. So just simply, if I displace the first mass to the right, like 1, the 2 spring will oppose the motion, right? So you can simply say the first mass, if displaced to the right, the 2 spring will oppose the motion. So K1 and K2, right? K1 and K2. K1, X1, K2, X2. X1 is 1, right? So Kx is force. X is 1, so K1 and K2. So what is the, okay, here, let me write here the first column. K1 plus K2. K1 plus K2. So K1 plus K2. Basically, the force when you apply a unit displacement, K1 plus K2, and because the displacement at 2 and 3 are 0. Therefore, 2 is the force at mass 1, which is defined as here. If the force is a stiffness. So K1 plus K2 is force at mass 1, and the displacement at 2 should be at mass should be 0. Therefore, there should be a reaction force to the mass 2 in order to make sure the displacement at mass 2 is 0. So there should be minus K2. Minus K2, and when K2 is a stationary, mass 3 definitely would be a stationary, so there would be no need to do anything, right? So I want to review the first column again, how to fill out the first column. For finding the stiffness, for the first column, you apply a unit displacement at mass 1, while you have to make sure the displacement at mass 2 and 3 are 0. And you have to find the corresponding forces, which is translated into a stiffness at the first column. So if mass 1 is displaced like 1 to the right, the K1 and K2 will oppose the motion. So K1 multiplied by 1 plus K2 multiplied by 1. So K1 plus K2 is the resultant force applied to the mass 1. So you just simply write K1 plus K2 and as a K11. K21, it means this force at mass 2 when there is a unit displacement at mass 1. In order, while we have to make sure displacement at 2 is 0. And since K2 is opposing the motion to the left, there should be a reaction force to the right. So you have to say minus K2. And once M2 is a stationary, M3 would be a stationary. So before going to filling out the second column, you have to use the reciprocity theorem in order to.
Sorry.
Yes.
Can you repeat for minus K2, please?
Okay. For basically the first column is there is a unit displacement at only 1, and the other displacement must be 0 in this approach in order to find a stiffness. This is the technique. So you have to make sure displacement at 2 and 3 are 0, while there is a unit displacement at 1, and K11 and K21 and K31 is the resultant forces. So the mass 1, if I displace to the right, K1 and K2 will go to the left, right? So you simply say K1 plus K2 is the force applied to the mass 1. However, if we want to make sure X2 is 0, there should be a stationary, the reaction force in order to neutralize these forces. So I just write minus K2, because K2 will oppose the motion for the movement of mass 1, and there should be a reaction in order to make sure X2 is 0. So no matter at what direction you displace the mass 1, to the left or to the right, there should be a reaction force to the mass 2 in order to make sure M2 is 0. And the only connection between the mass 1 and mass 2 is the stiffness K2. That's why I just wrote minus K2 is the reaction force applied to the mass 2 in order to make sure the displacement at mass 2 and mass 3 are 0. And once the M2 is stationary, therefore, there is no reaction force applied to the mass 3, and the stiffness, the force at mass 3 would be 0. Or simply, I could say K1 and K2, there are two forces applied to the mass 1. There should be minus K2 in order to make sure the mass 2 is stationary. Because
perfect, thank you.
Okay, you're and also for the influence matrix, as we hear, for example, for A33, I just wrote that F1 should be 0, F2 should external force, and here there is a similar approach. You have to make sure that a stiffness are 0 at the other forces. So before filling out the second column, you have to use, it's better to use reciprocity theorem. So this array is K12, which is going to be equal to K21. So you have to, right here, rather than in the matrix, you have to say, according to the reciprocity theorem, Kij is equal to Kji. Therefore, K12 is equal to K21. So you can easily just say minus K2 here. I just erase here in order to prevent it becomes very crowded. So minus K2 here, and also K13 here. This matrix K13 is simply K31. K31 is this matrix K31. So this will go here. And the next matrix, next array you have to fill out is K22. K22, it means M1, K1, 2, M2, okay, K4, K3, X1, X2, X3. So for the second column, we apply a unit mass at 1, while make sure the displacement at 3 and 1 should be 0. As soon as I displace the mass to the either to the left or right. So if I displace to the right, these two springs will oppose the motion, K3 and K2. So K2 and K3, yes, K2 and K3. So here you just simply write K2 plus K2 plus K3. The force, if I displayed mass to either to the right or left, K2 and K3 will oppose the motion. K2 plus K3 therefore would be the resultant force, which is called K22. So however, in order to make sure K3 mass 1 and mass 3 is stationary, so there should be a reaction force here and reaction force here. So in order to make sure M3 and M1 is the displacement are 0, there should be minus K3 applied to the M3 and minus K2 applied to the mass 1, right? Minus K3 applied to the mass 3, minus K2 applied to the mass 1. So here, minus K3 applied to the mass 1 already obtained, and minus K3 applied to the mass 3. Minus K3 here, minus K3 applied to the mass 3. There's a reaction, and there's action, and there's a reaction force. This leads us make sure X3 is 0. This is the technique, this is how we fill out the stiffness matrix. So as soon as you fill out the second column, therefore you could easily go for, you could obtain this one, K23. So K23 you could say is equal to K32. It is not necessary to obtain K23 by the same approach. You can take advantage of reciprocity theory. So K23 is K32, just simply plug in minus K3, that's it. The only array you need to obtain is the last array, K33. So K33 K33 and M1.
It's going to be K3 plus K4, right?
Exactly, yes, it is necessary to, yes, just simply, exactly. If I displace the mass 3 to the right, K3 and K4 will oppose the motion. So you will write K3 plus K4, and there should be a minus K3 in order to neutralize the displacement of M2. So exactly, yes. You're right. K3 plus K4. Just by taking a look at the system, you could say, so M1, K1 plus K2, M2 should be minus K2, M3, 0, and M2 is K1, K2 plus K3, two reaction force minus K1, minus K3, minus K2 and K3. And for the last column, if you displace M3, there exactly K3 plus K4 is K33. And there should be minus K3 applied to the mass 2 in order to make sure the displacement at M2 is 0. So let me finish it here. It's better to mass 1, mass 2, mass 3 here. The last part, X3 is 1, X2 is 0, X1 is 0. So K1, K2, K3, K4. So mass 1, mass 2, mass 3. So if you displace mass 3, K3 and K4, these two forces will oppose the motion. And there should be a reaction force to this one in order to make sure X2 is 0. So minus K3 would be here and 0 for this one, because M2, once M2 is 0, displacement, automatically the displacement of mass 1 would be 0. So here, 0 here, minus K3 here. So this is how you have to basically fill out the stiffness matrix and influence matrix and a stiffness matrix. So six point 4. So if you know the principle, you could go for any problem like 6.4.
Sir, just a quick question. So in the previous exercise, we were we were applying forces and see the displacement. So the springs were acting as they were in series, right?
Exactly.
And in this case, they act like they were in parallel?
Neither parallel or
Series, okay.
there is just a technique here. You have to make sure we apply a unit displacement at each mass and make sure the other displacement are 0 and just go for forces, because F is Kx and K would be force.
So it's ruled by this rule. So it's
exactly
just by applying the rule. It's not because they're in series or in parallel.
Right, exactly right.
Okay.
Right. So as soon as you know how to fill out A and a stiffness, you can easily go for other problem like 6.4.
And sorry, the previous matrix was the K matrix, which is equal to A minus 1, right?
Exactly. Yes, exactly.
Okay.
Exactly. Right.
And the only way to find the matrix A, I cannot find it from the matrix K, right? I'll have to
generally when
find
there
A,
are exactly.
I really need to apply forces.
Right. Generally, when there are two sides, the left and the both side of this system is constant, it is difficult to go for directly obtaining the influence matrix. And it is better to obtain the stiffness and then take inverse. But the question, the exam is very clear. It's not like this very complex. You will just definitely be given the appropriate problem and just ask you to go for obtaining the influence matrix. Just one person maybe should be difficult like this. It is better to obtain a stiffness and go for inverse and find A. But make sure you know how to relate. In one case, one person, maybe there should be a problem. You have to know how to reach from K to A and how to reach from A to K. Just take inverse, that's it.
Okay, no problem.
Particularly and mainly you will be asked for influence matrix rather than a stiffness. I just wanted to complete the scenario, but mainly you will be asked for influence matrix. So 6.4 6.4. Determine the flexibility matrix for the cantilever beam shown here and calculate the stiffness matrix from its inverse. So everything is clear now. At first you have to obtain flexibility and then you have to take inverse to obtain a stiffness. So at first you must obtain the flexibility. There is no any other choices. So there is a cantilever beam like this.
So basically they're asking to find A, and then that means I found A minus 1, right?
Right. At first you have to find the flexibility matrix. You have to find A as step 1. And part B, you have to take inverse from A to find a stiffness, step 2. In this question, you have to, at first step, you have to obtain the A in flexibility matrix. And in the second part, you have to find the stiffness the stiffness matrix by merely and just taking inverse of A. That's it. So there is a cantilever beam which we could basically, if there is a, so let me just write here. So it becomes very, so here, so there's a cantilever beam here. Each section is L/4. If there is a unit force at this point, so we can model this cantilever beam by, this is a continuous mass, so we could just, for the sake of simplicity, it is given to us just for section 1, 2, 3, 4. It is written 1, it is written 2, 3, and 4. So you can say that, you can imagine we have a system of discrete masses, lump masses like this, M1, M2, M3, and 4. So M1, M2, the length between the each is given as L/4. So so nothing is given here after. This is the question. So we have to find the flexibility matrix. I just ask, since it is given 1, 2, 3, 4, I can assume and model this cantilever beam by 4 discrete masses, M1, 2, 3, 4. So in order to find the influence matrix, I have to apply a unit force and to see what is the resultant displacement at each masses, at each section. So there are 4 points, there should be their matrix should be like this: A11, A21, A31, A41, and A2, A12, A22, A32, and A42. So A13, 2, 3, A2, 3, A4, 3, and 1, 4, A2, 4, A3, 4, and A4, 4. So as I told you, at first step, I will go for the first column. So you have to focus only for the first column. Influence matrix. So first column. For the first column, we have to apply a unit force at M1 and obtain the displacement at M1, M2, M3. So therefore, I apply a unit force here, and I will see what is the forces, what is the displacement at 1, 2, 3, 4. In the cantilever beam, you know how to calculate the displacement. Suppose you have a cantilever beam and P is here, and as soon as you apply the force, there is a deflection. So this is going to be A11. So this is going to be A21. Displacement at 2 due to the unit force at 1. Displacement at 3 due to unit force at 1. Displacement at 4 due to unit force at 1. At first step, you have to go for A11. So in general, when we have in the material, strength of material, we have already know that when there is a cantilever beam like this, and there's a there's a P force at the tip, the deflection at the tip, like point B, like B, deflection at the tip, point B is PL cube 3EI, where E is elastic modulus of the beam, I is area moment of mass moment of inertia, right? And also the slope. The slope at the tip, also theta B, is PL squared over 2EI. 2EI. By these two formula, you can similarly obtain the deflection at any part of this problem. So therefore, A11 is force divided by a stiffness. Force is unit. Force is unit, and the stiffness is 3EI over corresponding L, which is L over 4 here, right? L over 4 cube, which is going to be L over 4 cube 3EI L cube 192 EI. So here, I mean, if you take a look at here, deflection is PL cube over 3 EI. Therefore, force is 3 EI over L cubed multiplied by deformation at the tip. So this is called a stiffness, right? A stiffness, deflection, and force. F is Kx. So I just apply this formula to this problem. So here, this length is L over 4. So A11 therefore is P over K11. P is 1, and a stiffness we have the formula 3 EI over L. L is L over 4 for this case, for A11, according to this formula K. And I can obtain A11 like this. And I can easily go above and filling out the A matrix here, A11 as L cube over so as soon as you obtain A11, you can go for A21. A21. So if you take a look at here, A21 is this length plus this length, right? This length is L over 4. This is L over 4. Multiply by theta, this angle, theta 1, 1. So this theta is the same for the first column because there is no any force at the other masses. No external force here, and no external force here. That's why the theta would be the same for all of them. Theta 1. Theta is the same. So for the first column, if I want to find A21, if you take a look at this part, you can go for A21. A21 is A11 plus L over 4 multiplied by theta 1. So how can I find? I know already what is A11. This part is done. L over 4 I know. And theta 1 or theta at the tip at the L over 4, theta 1 there's a formula like I wrote PL squared over 2EI. So for our problem at point 1, P is unit, L is L over 4, 2EI. Theta 1 is L squared over 32EI. This is also done. You can just plug in here. Therefore, A21 would be finally 2.5 over 192 EI. So just plug in here 2.5 192 EI. So this is also okay. So similarly, theta delta A31. You can find A31 from A21. So A31 is A21 plus this length. So A31 is A21 plus L over 4 multiplied by theta 11. Similarly, because the theta is the same at each part. So I can say A31 is A21, which already obtained, plus L over 4 multiplied by theta 11. A21 is obtained as 2.4 192 EI L cube plus L over 4 multiplied by theta 11, which is already obtained, L cube finally at the end A31 would be 4L cube 192 EI. So just simply plug in here. The last one, similar approach. A41 is A31 plus this length. Similarly, I can say A41 is A31 plus L over 4 theta 11. Theta 11 is the same for all of them. The same. It's the same. Just plug in at each part. So A31 already obtained. If you multiply theta 11 by L over 4, the resultant would be L cube over 128 EI. 5.5 192 L cube and EI. So we already done with first column. So by taking advantage of reciprocity theorem, we could further fill out the matrix without doing any formulation or any manipulation with the formula. So 5.5 so here so this will go here, right? A21, A12. This will go here, and this is also go for this one. And A2 by, right. So 1, 2, 3. 1. Okay, I made a mistake here. Okay, sorry. So
the first column is always like the longest in this kind of exercise, and then it's gonna get faster and faster since we'll have less.
pardon?
I said the first column in this kind of exercise is always like the longest to do,
Exactly.
and
The
then
rest
it's
is
gonna be faster and faster.
right. Exactly. The first column is very important. The rest is very easy. The rest will be very, very easy. So I made a mistake here. Sorry, I just, you're right, Vance. You're right, Yasin. And the first, oh, I made a mistake here. It's very complex. Right. You're right. The first column is the longest, requires longest calculation, and so according to, we have to write, according to the reciprocity theorem, Aij is equal to Aj1, therefore A12 here. A12 is equal to A21. So this will go here. Also A13 is equal to A31. This will go here. And also A14 is equal to A41. You can simply fill out oh no. Yeah, okay. So let me write down these two with the red color. Just simply for L cube 192 EI 5.5 L cube okay. We will go for also no. Okay, the next problem. Okay, we have to go for the next step is obtaining A22. At each column, we will start from AII, A11, A22, A33, A44. Right? The second column, we have to start from A22. The third, A33, the last, A44. So A22. Put unit load at point 2 and repeat the above procedure. One, two, three, four. Okay. A22. Displacement at 2 due to unit force at 2. Displacement at 1 due to unit force at 2. Displacement at 3 due to unit, sorry, I have to say, should have said, okay, displacement at 3 due to unit force at 2. Displacement at 4 due to unit force at 2. Displacement at 1 due to unit force at 2. So similarly, A22 easily is PL cube 3EI, the formula. So P is 1, L in the formula is L over 2 for the second mass, 3EI, therefore it would be L cube 24 EI. So you can go on L cube over 24 EI. So similarly, A32 is A22 geometrically. If you take a look at here, A32 is A22 plus this length. This length is L over 4 multiplied by theta 22. A32 therefore is equal to A22 plus L over 4 multiplied by theta 22. A22 is already obtained. However, theta 22 should be obtained as PL squared 2EI. P is 1, L is half L. Okay, so if I plug in here, therefore A32 is 7L cube over 96 EI. So here 7 L cube over 96 EI, and similarly A42, just simply A42 is A32 plus L over 4 multiplied by theta 22. Finally, it's going to be 10 over 96. So the second column is already finished. Second column is finished, 10 or 96 L cube EI. So we can also fill out further the matrix. A 2, 3 is going to be A 3, 2 according to the reciprocity theorem, right? So this is going to be this one. let me write by red, 7L cube over, and also A24 is equal to A42. So it is better to write this in the lower of the matrix. So because it becomes very crowded here. So this is going to go here. This will go here. 10 over L. I just wrote here in order to see, because it's difficult to go on up and down. So 10 L cube 96 EI. So the next step is AII, A11, A22, A33, A33. So I don't want to take your time and just simply, but the approach is the same. A33. A33 PL cube 3EI. P is unit. A33 can be translated as displacement at mass 3 due to unit force at 3. L for the third mass in this system is 3 over 4 L. It's 9 over 64. So A33 is going to be 964 L EI. So A34 sorry, A43 displacement at 4 due to unit force at 1. So this is again is going to be A33 plus this length. A43 is A33 plus L over 4 theta 33 theta 33 is PL squared 2EI two EI 9. Okay. So I already obtained A33, just plug in here. 9 over 64. Theta multiplied by L over 4, which is going to be totally 2728 L cube over EI. Okay, so 27 L cube over 128 EI. So according to the reciprocity theorem, this array, which is A3, 4, is going to be A4, 3, which is already obtained. So this should be go here. 27 L cube over 128 EI. And the last step is A44. So A44 is the basic formula I just mentioned at first. There's the unit force at the end, right? So A44 simply is PL cube so this is how you have to fill out this matrix. The last one, L cube over 3 EI. So if you have a question, Yasin, you can ask. And let me finish this chapter in the next session. But now if you have a question, I'm here to respond to your question.
No. So that means we found the influence matrix now.
Exactly, we are done with, okay, sorry, second part, the stiffness. So A is done. A is done. Okay, A is the second part, a stiffness is going to be A inverse. So you can factor out the constant number from all of the array. The constant number from all of the array is L cube 192. You could factor out this term and just so a stiffness is going to be this constant number because it is a number. You can factor out from all the array. So A inverse is 1 over determinant of A multiplied by adjunct matrix transpose of adjunct matrix. So adjunct matrix is just so for if A was 3 by 3, for example 1, 2, 3, 4, 5, 6, 7, 8, 9, and adjunct matrix. So for if A was like this, first for determining for obtaining the determinant, you can take one row or one column, plus, minus, plus, and say the determinant of A is plus 1. At the adjunct of A1, 1, you have to remove this and this. The left matrix is adjunct matrix, but for determinant, you have to calculate the determinant of the adjunct. Determinant of 5, 6, 8, 9, minus 2. Determinant of the adjunct for so here, this time you have to remove this and this. Determinant of the adjunct is 4, 6, 7, 9. So similarly, plus 3,
4, 5, 7, 9.
Yeah, 4, 6, 7, 4, 6, 7, 9. So this is the determinant, and the A inverse, if A was 3 by 3, would be 1 over determinant transpose of adjoint. So transpose of A star. A star is A star. So A star would be adjoint matrix. I think each of these is each array in the adjunct matrix is, so for example, this is the response of this determinant, for example, is suppose it's 5. 5 will go here. And the response of so 3 by 3, right? 3 by 3. So for each array, you have to find the adjunct and fill out the adjunct matrix and just take transpose to find A inverse. However, in this matrix is 4 by 4 and little bit lengthy, calculation is a little lengthy, and you have to find determinant of the matrix A, and the response, the final response I can give you, K is L cubed. Factor out this term. Just work with the number. Just factor out. At the end, you can multiply this by this matrix. So 6.3 minus 3.94, 1.48 minus 0.25 minus 3.94, 4.78 minus 3.19 minus 3.3 minus 0.25. What happened? This one. Okay, this one. So for the determinant, you have to solve some problem.
Yeah, it's okay for the rest, I think.
Okay,
Yeah.
thank
So
you very much for today.
No problem, thank you.
If just solve some problem and just bring your question next session. I will try to finish this chapter next session, and we will finish the influence matrix next session, and then we'll go for, I will ask your professor what is the latest part and to see what is the next session. I think the chapter 12 is the next chapter.
Yeah,
The numerical, right.
But thank you very much for today.
You're welcome. Have a great day.
You too.